Hi, I'm Jamie Baxter, instructor for A&P2. We're going to continue on. This is the third part of our lecture on equilibrium in our body. And we just got done talking about sodium and potassium balance, and now we're going to talk specifically about acid-base balance in the body. Potassium is strongly linked to this, and since potassium is strongly linked to this means sodium is linked as well. It's all interconnected, and it all relates to one another. And as we know, just from talking about all of our other body systems, if our blood pH is off, this is not a good situation for our body. So we need to understand the mechanics of how our blood pH and extracellular pH is regulated. And this is going to interplay several body systems together, working together to either get rid of extra hydrogen or retain extra bicarbonate. So let's take a look closely at how acid-base balance works. There we go. So overall acid-base balance is when our hydrogen production and hydrogen loss, I'm saying hydrogen, I really should be saying hydrogen ion. The hydrogen ion production and hydrogen ion loss and the pH of the body are within normal limits, right? So that it's maintained. How are hydrogen ions produced? Well, this should sound familiar to you. Metabolic activities like carbon dioxide to carbonic acid, right? This happens during aerobic respiration. This happens in our red blood cells. Lactic acid from our glycolysis is going to, lactic acid, if there is anaerobic respiration going on, from glycolysis is going to lead to a buildup of hydrogen ions as well. There's also a constant production of these in general, just as our body is mostly transporting carbon dioxide as bicarbonate. So a buildup of hydrogen ions from that carbonic acid. So let's see how hydrogen ions are lost. Our respiratory system eliminates hydrogen ions because of when we release carbon dioxide, just that whole feedback loop. Remember this equation where we have water plus carbon dioxide reacting with carbonic anhydrase gives us our carbonic acid. Carbonic acid dissociates into bicarbonate and a hydrogen ion. So we have that opposite reaction taking place as our carbon dioxide is being released. Our bicarbonate and hydrogen ion combine to form carbonic acid. Carbonic anhydrase are going to separate the two and form carbon dioxide and water. If what I just said to you is Greek, that means that you didn't learn it the first time when we did it in our respiratory system. Take the time, pause the video, go back, listen to what I said, write it down, or go back to a respiratory chapter. I forget which one it was, chapter 20, maybe it was chapter 20. Can't remember. Whatever our respiratory one was, I get the chapter numbers mixed up in my head. Go back and relearn it then. Super important to understand that equation that I just ran over. Either way, excess hydrogen ions are excreted from the kidneys. We learned that in the last chapter. And there are, of course, buffers that are going to temporarily store hydrogen ions, basically removing them from circulation. This is going to affect our overall pH as well. So here's all of the key parts. Respiratory system, our urinary system, buffer systems in place, and then the tissue cells. So the tissue cells are actively generating carbon dioxide and hydrogen ions, right, through glycolysis and aerobic respiration, putting them all in the blood. That's how everything, gets anywhere in our body. Stick it in the blood. What is our blood going to do with it? Well, the red blood cells are going to react, right, producing all those extra carbon or extra hydrogen ions being released in our respiratory system. Too much of it being produced, we're going to release it in our urinary system. Too much of it still around, then our buffer systems are going to help absorb the extra hydrogen ions so that our blood pH doesn't drop. So there are different types of acids that affect our pH balance, right? These are acids that are going to release hydrogen ions into the solution if our blood pH rises, right? If we get too alkaline. Fixed acids do not leave a solution. These remain in the body fluids until they're excreted at the kidneys. An example of this would be sulfuric or phosphoric acids. These are generated during amino acid catabolism or phospholipid catabolism or nucleic acid catabolism. So remember, phospholipids will break down into fatty acids. So basically, anytime we're breaking down anything other than a carbohydrate in our body, a nucleic acid, a fatty acid, and an amino acid, we're going to get sulfuric and phosphoric acids as a byproduct. This is why our body chooses to use carbohydrates as our main source of energy. We don't have all of these acids being produced, right? We're just producing carbon dioxide and water, right? Easy peasy, get rid of them, right? When our body is in a post-absorptive state where we have to break down amino acids or phospholipids or nucleic acids, we're going to have to deal with the consequences. And that is when we have a buildup of sulfuric and phosphoric acids. So we also have organic acids that are produced. These are typically byproducts of cellular metabolisms. These would be like lactic acids and ketones that we mentioned a few chapters ago. Most of these are metabolized and broken down pretty quickly, so there's no significant accumulation. Remember, lactic acid is recycled in the liver through that Cori cycle. There's also volatile acids. These can leave the body by entering the atmosphere at the lungs. So carbonic acid is our big example of a volatile acid. This is exchanging with the environment. So fixed, organic, volatile. No examples of each and what they are. You can pause the video here, go back and review this section. Let's talk specifically about pH. Typically, the ECF pH is between 7.35 and 7.45. Extremely dangerous to go outside of that range, and meaning like coma and death outside of that range, right? So changes in hydrogen ion concentrations are going to alter the stability of our plasma membranes, right? They're going to change the structure of our proteins. Remember, proteins are very reactive to changes in pH and temperature. They denature and they stop working, they fall apart. Our body is mostly proteins. So if we're changing our blood pH, we're changing all of our body's proteins. Very, very dangerous. That's going to also change our enzymes. Enzymes are proteins. So if our enzymes can't work to do our metabolic processes, big problem there. They also have major effects on our nervous and cardiovascular systems. So a blood pH below 6.8 or above 7.7, very, very fatal, dangerous. Don't mess with it. So let's talk just some general terms related to acid-base balance. This is like review from like chapter 2, if I remember correctly. pH, just the basic concentration of hydrogen ions in a solution. It's a logarithmic scale. So the numbers aren't quite equal to one another, but that's the general idea. A neutral pH is a pH of 7. Acidic is when your pH is below 7 and you have lots and lots of hydrogen ions in the solution. A basic or alkaline condition is above 7, and that's where we have hydroxide or OH ions, not hydrogen ions. Acid-base, a salt, is a ionic compound that has a cation and a hydrogen ion associated with it. And a buffer is a solution or a substance that is counteracting the changes in pH in a solution. And we've talked about a few buffer systems. We're going to get into more of them in this section. So let's talk about conditions that persist in the extracellular fluid compartment. Acidosis, a physical condition when your pH is below 7.35. It can be deadly. Your central nervous system function is going to deteriorate. Your cardiac contractions are going to grow weak, very irregular. Vasodilation is going to cause your blood pressure to drop, can lead to circulatory collapse. Alkalosis is where you're above 7.45 and can be dangerous. This is much more rare. Our body tends to be more on the acidic side just because we accumulate acids from our metabolic activities. So this is looking at that normal range, and anything outside of that range is super dangerous. Let's talk about how carbon dioxide plays a role in pH. So carbon dioxide is our main, I don't want to say determinant, ingredient, I don't know. The main thing related to pH in our body, right? The partial pressure of carbon dioxide is, there we go, the first sentence on this slide, maybe I should just stick to the slides, duh, Jamie, is the most important factor in affecting pH of all of our body tissues. I try not to read the slides if you haven't figured that out. But either way, partial pressure of carbon dioxide, the number one determining factor of pH in our body. Carbon dioxide combines with water, right? We have that whole reaction that I described earlier, creating carbonic acid, which dissociates into bicarbonate and a hydrogen ion. It's reversible, thank goodness, so that we can get rid of all of that carbon dioxide. So there is an inverse relationship between carbon dioxide and pH. Now, this is where it gets tricky because you have to pay attention to the wording of things. When things say they're highly acidic, what they're really meaning is that they're low pH, right? Because acidic things have a low pH. So you can think of it like this: an inverse relationship between carbon dioxide concentration and pH. In other words, as carbon dioxide goes up, the pH goes down, which means it's more acidic. Or you can think of it like this: as the carbon dioxide concentration increases, the acidity increases, meaning more carbon dioxide, more acidity. It's up to you how you want to make that association in your head, but don't get those terms confused. Acidity, which is a term very commonly used, is not the same as pH, right? It's actually opposite. When you're saying the pH decreases, you're saying the acidity increases. I hope I didn't confuse you. I shouldn't have confused you at this level of your education. So there's an inverse relationship between partial pressure of carbon dioxide and pH. Increase in pH, or increase in carbon dioxide, decrease in pH, decrease in carbon dioxide, increase in pH. Boom. Here you go. Here's that nice little happy equation that I was referring to earlier in terms of hydrogen ions and water and carbon dioxide levels. It's an inverse relationship. You should have that equation memorized for sure by this point. Understand what those components are and how they interact. So we have mentioned that bicarbonate buffer system in the body, but we haven't talked about all of the buffer systems in the body. So there are a few different buffer systems that act in the body, generally consisting of a weak acid and the anion that is released by the dissociation of that weak acid. So the anion is going to function as a weak base. So you have this relationship between a weak acid and a weak base kind of ebbing and flowing back and forth depending on what your body needs. If your body has too many hydrogen ions, then that weak base is going to absorb the extra hydrogen ions. If you don't have enough hydrogen ions, then that weak acid is going to dissociate and release hydrogen ions. It's kind of this ebbing and flowing of hydrogen ions being either soaked up by the weak base or released by the weak acid. Does that make sense? Hopefully. So the weak acid and the anion are always in equilibrium, and adding hydrogen ions to that equation is going to disrupt the equilibrium. Removing hydrogen ions is also going to disrupt the equilibrium, and obviously they have opposing effects on our pH. So this is just a general review of buffer systems, right? You have your weak acid and weak base exchanging hydrogen ions to either absorb extra or release depending on what the overall pH is in your body. You can pause the video here, go back and review this section. In the next part that I'm going to flip to in a second, we're going to talk about the different types of buffer systems in our body. We understand what they are now: weak acid and weak base exchanging hydrogen ions. Let's go ahead and move on to talking about what these buffer systems are. They all bind to hydrogen ions temporarily using that weak base system that I just mentioned. The hydrogen ions are not eliminated, they're just absorbed, and then they can be released or absorbed or released depending on what the overall pH is or what the overall hydrogen ion concentration is, because pH is a hydrogen ion concentration measurement. The phosphate buffer system uses buffers of pH in the ICF, intracellular fluid. This is the major one inside of our cells. We also have a protein buffer system and the carbonic acid bicarbonate buffer system. There they are. Inside of our cells, we have the phosphate buffer system. Guess what the phosphate buffer system uses? It uses ATP. Ooh, remember that guy? Protein buffer systems like hemoglobin acting as a buffer, or amino acids acting as a buffer, or plasma proteins acting as a buffer are present in the ICF as well as the ECF, and then strictly in the ECF is our carbonic acid bicarbonate buffer system, which we've talked about already. So these protein buffer systems, these contribute to the regulation of pH inside and outside of our cells, usually binding excess hydrogen ions. The amino acids in our proteins can bind to hydrogen ions that are accumulating. The carboxylate group, COO, can form a carboxyl group, COOH. The amino group can form an amino ion, NH3. And the R groups can also bind to hydrogen. And this is the majority of the buffering that goes on with our proteins. So remember, amino acids have the functional group or the R group, the amino group, and the carboxylate group. So either one of those can bind to a hydrogen ion to help absorb extra hydrogen ions. There you see the protein buffer system in action. You have your amino acid here at a normal pH, and it can absorb an extra hydrogen ion if it needs to. And if there's lots and lots of hydrogen ions in the solution, well, guess what? All of these parts can absorb extra hydrogen ions. So you can have your amino group absorbing an extra hydrogen ion, your carboxyl group absorbing an extra hydrogen ion, as well as your R group. So very functional inside and outside of the cells. You also, specifically hemoglobin buffer system, this is the only intercellular buffer system that has an immediate effect on the overall pH of all of our body fluids. And your red blood cells are absorbing carbon dioxide from the plasma. We know this already. The carbon dioxide is converted into carbonic acid, and the carbonic acid dissociates, and the hemoglobin absorbs those extra hydrogen ions. Because if the hemoglobin didn't absorb those extra hydrogen ions, your blood cells would be like extremely acidic, right? So hemoglobin absorbs those extra hydrogen ions in exchange, and then when the reverse reaction happens, it releases those hydrogen ions. So in that word, or in that respect, hemoglobin is acting as a buffer. Just trying to figure out, my phone's going crazy here. Okay. In the lungs, the process is reversed, straight to release that carbon dioxide into the alveoli and get it on out of the body. Here it all is, right? So here you have our tissue cells releasing carbon dioxide, going into our blood plasma, our red blood cells soaking up that carbon dioxide, converting the carbon dioxide into carbonic acid and bicarbonate, and then that extra hydrogen ion from the carbonic acid is being absorbed by the hemoglobin. So hemoglobin is acting as a buffer inside of our red blood cells. This is like a double buffer system, right? So we have our bicarbonate buffer system working here, and we have our protein buffer system working here. Boom. Because remember what happens with the bicarbonate? The bicarbonate is shifted into our blood plasma with a chloride ion, right? That's the chloride shift. The chloride ion comes in and the bicarbonate gets pumped out. And then the opposite reaction happens in the lungs to release that carbon dioxide. These are the individual slides. So that carbonic acid bicarbonate buffer system is the most important buffer system in the extracellular fluid. It involves those reversible reactions that we've been talking about, I don't know, for 20 or 30 minutes now, right? It protects against the side effects of all of those acids that's generated by our metabolic activities, taking the released hydrogen ions generated by carbonic acid, combining it with hydrogen ion and bicarbonate. The carbonic acid dissociates into water and carbon dioxide, and then we typically have a bicarbonate reserve. This is left over in the body fluids in the form of sodium bicarbonate. So sodium can bind to carbonate to form sodium bicarbonate, and it basically waits around for extra hydrogen ions for it to soak up. I say soak up. I hope you understand that it's not actually soaking anything up. It's just the visual that I think of. It's grabbing them out of the solution and holding on to that to remove them from the solution. Here's the overall thing, right? Sodium bicarbonate all the way over there on the right, dissociating into sodium and carbonate. That bicarbonate goes back into our red blood cell, adds on or gets added to a hydrogen ion. The hydrogen ion is coming from metabolic activity, right? Combines to form carbonic acid. Carbonic acid dissociates into I'm talking too fast. Carbon dioxide and water, and carbon dioxide is then diffused through the lungs and exhaled. Really good flowchart opportunity here on this slide. I always suggest recopying and recreating these flowcharts in your notes. It's more visual. It's going to make you think more than just looking at the slide and saying, oh, yeah, I get it. I promise you, you don't get it if you're just looking at the slide. You need to write it out. All right, there are some disorders that are related to metabolism and acid-base issues. So these typically will result from either having too much or not enough fixed or organic acids being produced and released. The bicarbonate buffer system is going to protect against those disorders, but obviously it can only work so well if the disorder is so extreme it can't keep up. There are respiratory acid-base disorders. These are a result of an imbalance of carbon dioxide generation and elimination. So carbonic acid bicarbonate buffer system can't protect against this. There's just too much going on. The imbalances have to be corrected by a change in either the rate or the depth of our respiration. And all of that is regulated in the medulla oblongata, right? The VRG and the DRG, remember those? So our medulla oblongata is going to basically say, whoa, we have too much carbon dioxide or not enough carbon dioxide, so we need to change how quickly or how deeply we're inhaling and exhaling to get our carbon dioxide levels back down, because our buffer systems can only do so much. You can pause the video here and go back and review this section. Let's talk about some metabolic conditions that result from an acid-base balance. So there's respiratory conditions that result from acid-base balance, but there's also metabolic conditions as well. Metabolic acidosis develops when a very large number of hydrogen ions are released by either organic or fixed acids, and then the pH decreases. So this, the overall response is a respiratory response, where you're going to increase your respiration rate, lowering your partial pressure of carbon dioxide, converting more carbonic acid into water, getting that carbon dioxide out of the body, right? But there's also a renal response. This is going to occur in the PCT, the DCT, as well as the collecting system, where you're going to secrete more hydrogen ions into the urine. This is going to remove carbon dioxide from the body as well, because you're reabsorbing more bicarbonate to help replenish your bicarbonate reserves in that case. So here's a whole schematic view. You have too much hydrogen ions accumulating, right? Maybe you're eating something or drinking something highly acidic. So your bicarbonate buffer system is going to work, converting to carbonic acid, carbon dioxide, exhale it, right? The other thing that your body's going to do is secrete the hydrogen ions at the kidneys. So this is going to cause your urine to drop in pH, but as your body is releasing hydrogen ions, it's reabsorbing bicarbonate ions, and so the bicarbonate can float around, soak up any extra hydrogen ions that are in the blood to help act as a buffer as well. So it's kind of a triple threat. So overall review of hydrogen ion removal and bicarbonate production in the kidney tubules. Of course, you have the same reaction going on that was in our red blood cells, carbon dioxide and water, reacting with carbonic anhydrase to produce carbonic acid, dissociating into bicarbonate and hydrogen ions. Hydrogen ions are being counter-transported with sodium and co-transported with chloride, and on both sides, either in the ICF or ECF. So as we're getting rid of our hydrogen ions, we're bringing in sodium ions. And if we're bringing in sodium ions, we're also removing potassium ions, right? Because sodium and potassium always move opposite of each other. They're kind of like, you know, ex-boyfriends and girlfriends at a club or something. They just kind of avoid each other by all means. And what else did I want to say about this? I think that's it. So metabolic alkalosis is a little bit different. This is when large numbers of hydrogen ions are removed from our body fluid. So this is raising our pH. So our overall renal response is going to include rate of hydrogen ion secretion declining, right? We're going to retain hydrogen ions. Tubular cells are not reclaiming bicarbonate. We're going to excrete bicarbonate. Collecting system transports bicarbonate into that urine, and releases hydrochloric acid into the extracellular fluid. So it's basically the opposite of what we just did. So our responses also include a respiratory response. Everything includes, when we're talking about alkalosis and acidosis, everything is going to include a respiratory and a urinary response. So the respiratory response is a decrease in respiration rate, which is going to raise our partial pressure of carbon dioxide levels. It's going to allow carbon dioxide to accumulate, converting more carbon dioxide into carbonic acid, which is going to get our pH back down to where it should be. So the renal response in the PCT, DCT, and collecting system, conserving more hydrogen ions, reabsorbing them into the ECF, and excreting more bicarbonate. It's just the exact opposite of what we just did. Removing hydrogen ions from the body, we are going to have this elevated pH level, a very acidic condition, and so we are going to respond by elevating, or rather decreasing our respiration rate to elevate our partial pressure of carbon dioxide, which is going to cause a buildup of hydrogen ions in the body to get our pH back up. This slide, just so you know, is misnamed. So at the top it says response. I was looking at it kind of confused. This says responses to metabolic acidosis, but it's actually alkalosis in the depiction. So that just that little top corner is incorrect if you print out these slides and use them for the lecture. You might want to change that. Okay, so overall steps in actually removing the bicarbonate and producing the hydrogen ions, it's the exact same thing as before. Here we're soaking up carbon dioxide from the ECF and tubular fluid of the kidneys, converting it into our carbonic acid. And in this case, we are secreting our bicarbonate and secreting our bicarbonate into the tubular fluid and secreting our hydrogen ions and a chloride ion, because of chloride shift, into the extracellular fluid to get our pH back down, to get our acidity back up, I should say. You can, I think I am going to pause the video. We only have 10 more slides. Never mind. You can pause the video here and go back and review this section about alkalosis and acidosis. We just have a few more topics to discuss in this chapter, and then I have a few of my notes that I just want to go over with you to make sure that you understand everything that we went over. So overall, respiratory acid-base disorders are resulting from an imbalance between the rate of carbon dioxide generating in the body tissues and how much we're getting rid of at the lungs, or the elimination at the lungs. This cannot be corrected by the carbonic acid bicarbonate buffer system. We said this already. So with respiratory acidosis, the rate of carbon dioxide exceeds the rate of carbon dioxide removal, right? So you have too much carbon dioxide in the blood. This is going to shift the carbonic acid bicarbonate buffer system to the right, so it's going to cause it to generate more carbonic acid and more hydrogen ions. Our bicarbonate is going to, our bicarbonate goes into the bicarbonate reserve, soaking up extra sodium ions. Excess hydrogens have to be tied up by other buffer systems like the proteins, and then excreted by the kidneys. So the underlying problem cannot be corrected without a change in respiration rate. So you have to change your respiration rate during respiratory acidosis. Here you go. You have your buildup of hydrogen ions, and so you're going to break into your bicarbonate reserve, release bicarbonate from sodium bicarbonate, absorb those extra hydrogen ions, convert it into carbonic acid, convert carbonic acid into carbon dioxide, and release it at the lungs. With respiratory acidosis, how do we get back to homeostasis? We're going to increase our respiration rate. This is going to increase the amount of hydrogen ions that are excreted at the kidneys and the reabsorption of bicarbonate ions to further reabsorb hydrogen ions in the blood, and other buffer systems can help absorb those extra hydrogen ions, specifically the protein buffer system. This is how it all works together. I strongly suggest taking this slide, breaking it down into its parts. What do we have here? We have a normal pH, but then hypoventilation is going to cause an increase in partial pressure of carbon dioxide, which is going to cause a decrease in pH. So what do we have? Decrease in blood pH, we're going to have a buffers bringing our hydrogen ions, are binding to our hydrogen ions. The increase in rate and depth of respiration is going to help decrease the amount of CO2 in our body, and we're going to increase our hydrogen secretion at our kidneys, increase bicarbonate reabsorption at our kidneys, overall decreasing our partial pressure of carbon dioxide, decreasing our concentration of hydrogen ions and bicarbonate, increasing our concentration of bicarbonate ions, getting our blood pH back to normal. With alkalosis, the rate of carbon dioxide elimination is too high. So this is relatively rare, but it can be severe. In most cases, this is our hyperventilation state. This is self-limiting because you're going to faint and then go back to normal. So respiratory rate returns to normal levels once you pass out. This is going to shift our carbonic acid bicarbonate buffer system to the left and allow our hydrogen ions to be removed as carbon dioxide is exhaled and water is formed in that bicarbonate buffer system. So here you have our bicarbonate reserve being added to, and again, our carbon dioxide being eliminated at our lungs. So overall respiratory response is a decrease in respiration rate in alkalosis, decrease in hydrogen ion secretion at the kidneys, an increase in excretion of bicarbonate ions, and all of the other buffer systems are going to be releasing their hydrogen ions to get our blood pH back down to where it needs to be. And so our buffers, this is just the overall review here, right? Buffers are releasing our hydrogen ions like the bicarbonate buffer, the carbonic acid, overall increasing our hydrogen ion concentration. We're going to decrease the rate and depth of breathing to increase the amount of carbon dioxide in our blood. We're going to decrease the amount of ions that are being secreted at the kidneys, and we're going to decrease the amount of bicarbonate reabsorption at the kidney. So that's going to lead to fewer hydrogen ions being removed and fewer bicarbonate ions available, which is going to increase the hydrogen ion concentration in the blood, which is going to decrease our pH, which is increasing our acidity, which is getting us back to where we need to be. Boom, we did it. Other things that I wanted to mention here. I think I did all of this, actually. Our three main buffer systems. This is just general review, right? Three buffer systems, the protein, the bicarbonate, the phosphate. You should make sure that you know those. The two main systems in our body that are regulating pH, respiratory and urinary. I would do a big graphic organizer of each. Have at the top regulation of pH, boom, respiratory, boom, urinary, and then each have a scenario, right? So off of respiratory, say alkalosis, acidosis. Off of urinary, alkalosis, acidosis, and then have the responses to each on that graphic organizer. Like I said, I just think graphically like that. I like to think like that. So there is the last slide for your own review. I give you a little scenario there. Your book also has some questions at the end of the chapters for you to review, especially if you're confused on acidosis and alkalosis. I strongly suggest doing that. There's also on Mastering A&P a little link that says case studies. Ooh, it's kind of like the case studies that I give you, but they are a little bit more in depth. And there is, I think, your packets that came with your textbook have it's called the applications manual. It's kind of like a case study guide, and in it is descriptions of all of these cases, because this chapter is really like the cherry on top of our sundae when it comes to A&P. This pretty much concludes everything. We still have reproductive to cover. However, reproductive doesn't really add anything to the mix. This chapter with acid-base balance should solidify your understanding of everything that goes on in your body. So in other words, if you're a note card person, I bet at this stage in your A&P game, you probably have 2,000 note cards on A&P terminology. You should be able to pick one up and another one up randomly and connect the dots. That's one of the best ways to study for your A&P final exam, or even for any of your nursing school exams or future exams that you're taking. See if you can relate those terms together. Don't learn the terms in isolation. We want to create a big picture understanding of what's going on in the human body. So if you take, for instance, the basal lamina, right, which is a term that we talked about way back in like chapter 3, right, and you relate it back to respiratory alkalosis. Well, how do those two terms relate together? Well, right, I really challenge you to do that and come up with how those terms relate. Well, basal lamina is the cement that glues two epithelia together, or two types of tissues together, and in respiratory what did I say? Alkalosis, acidosis, doesn't matter. We're changing the amount of carbon dioxide that's being released by the body, and that carbon dioxide has to pass through our respiratory membrane, and our respiratory membrane includes the capillary lining of our blood, as well as the alveolar capillary, which is held together in place by basal lamina. Boom, done. Right? See if you can connect any dots together, all random terms. Go back to chapter 5, chapter 6, pick a term out of it, and then pick something that we just talked about in this chapter and see if you can connect the dots, right? If you're not a note card person. Because at this stage in the game, your puzzle is complete. You should have a very big mural painted in your mind of everything in the human body and how it all works. If you don't, you probably skipped something along the way. You probably faked your way through a topic and you ended up here in time, but you're not here in knowledge. So I suggest going back, reteaching and relearning that substances, or that topic rather. That's one of the great things about taking an online course is you can go back and watch the video, right? You don't have to, I mean, you can ask me questions. I would love for you to ask me questions, but the videos are there for you. All the knowledge is there. It's just up to you to understand what it is I'm trying to communicate to you. So if you don't get it, reach out to me. I want to help you. I want you to be successful. I want all of you to go on to successful careers and successful courses after this class. So please reach out to me. Let me help you. Help me help you. All right. Sorry, I kind of got off tangent, but I kind of get a little nostalgic this time of the semester because it's almost over. We only have one more chapter to go. And really, I always feel that this chapter is the icing on the cake, so to speak, when it comes to our understanding. So if there's something that we've covered along the way, even last semester in A&P world, that you just never really got, now's the time to ask, because reproduction is a quick, easy chapter. I'm saying it's easy. It's really not. There's hormones involved and there's systems involved in physiology. But when it comes to the overall picture of how the body works, you should pretty much have an understanding at this point. All right. Have an awesome day. Bye.